I want to talk about one more kind of quirk with phase diagrams and phases overall, supercritical fluids.
The final part of the phase diagram we want to talk about is called the critical point. So you may have noticed on previous phase diagrams, this is the one for water down here, the line for the liquid and gas coexistence just ends. At some point in time, it just ends. The solid liquid line does continue on forever. But the line between distinguishing water, the liquid water and gas phase water just ends at 374 degrees Celsius. This is called the critical temperature. Above this temperature, there is no distinction between the liquid and vapor phase. Everything above that temperature, all water, is called a supercritical fluid. So what's going on here is if we think about at the molecular level, liquids, the molecules are moving around each other close together. In a gas phase, the molecules are freely moving around far apart. So the distinction between gas and liquid is the space between molecules. As you get to really high temperatures, molecules just start moving really quickly. They just start kind of bouncing around more and more. And when they're moving faster, they're colliding with each other and making more room around themselves. Conversely, at high pressures, those gas molecules are getting pushed closer and closer and closer together. And so eventually you just get to a state where the liquid molecules, the molecules are really pretty far apart from each other. And in the gas, the molecules are really close together. And so they become indistinguishable. They become this supercritical fluid. This happens for every single compound at a certain temperature above. Once you hit a certain temperature above that, you reach a supercritical fluid. Gases and liquids are both fluids because they flow, and so this also flows like a fluid.
Now we can actually look at what supercritical fluids look like. So this GIF we have right here, this image, you'll note there is a horizontal line that is marked on the viewer or the view window, and that is showing the surface of the liquid. And so when we don't have below the critical temperature, we have a liquid and a vapor phase, and the surface of the liquid divides those two phases, right? So you have a liquid that's visible and the vapor. When you get something that is supercritical, when you go supercritical, you will note there's still that same horizontal in a different spot, but there's a horizontal line that's drawn on the viewfinder. That is the liquid surface at the beginning of what's going on here. And basically the temperature and pressure are changing such that we are going above the critical temperature. You can see there's a thermometer kind of through the back. You can kind of see through the liquid. This is CO2 in this right here. And you'll note that basically that liquid, that surface just disappears. You get what looks like boiling, right? It gets all like cloudy. It looks like you're forming bubbles. It's similar to boiling. It's just going to become a supercritical fluid. And now at the end of the GIF, so we see it looks like it's boiling. And then these words, once the words disappear, we'll note there's no more surface of the liquid. There's like something right here. That's just the top of the thermometer. So that's the top of the thermometer, that's in the background. That's not any sort of surface. There's just one big full kind of fluid that's filling that container. And so we can see there's a couple different behaviors of supercritical fluids on display here. One, they flow with gravity like a liquid. So you can pour them like a liquid, but they fill their container like a gas. So one of the things to note from those filling the container like a gas, flowing like a liquid, supercritical fluids exist under extreme conditions. You're never going to see them like just out in the lab or anything like that, where those sorts of like characteristics like wouldn't work together. They're only under these extreme conditions where this isn't like a high pressure cell with some crazy temperatures going on and things like that. So this case, this is it feels bizarre because it only happens under conditions that you have never experienced and never will experience because they're so extreme.
Supercritical fluids have a decent number of applications. They're really useful in that they have low surface tension. Gases have no surface tension. And so similar to that, they have low surface tension, so they can flow, they can fill space. They can also importantly act like solvents. That's what liquids do. They tend to dissolve things. So supercritical CO2 is relatively easy to produce as far as you don't need crazy temperatures or pressures, so you can do it relatively safely. And so supercritical CO2 is used, that's actually how you decaffeinate coffee. So caffeine-free coffee. You can't like boil out the caffeine because you remove the coffeeness of the coffee. So what you do is they basically wash coffee beans in supercritical CO2. Importantly, it acts like a gas with low surface tension, which means the molecules of CO2 can penetrate the coffee beans, and then they can also kind of act like a liquid and dissolve the caffeine. They preferentially dissolve caffeine. We'll learn why they preferentially do that. They do take other things with it. Decaffeinated coffee does have less coffeeness to it than normal coffee, but they just flow right out. And importantly, they don't degrade the bean. And it's just high temperatures, and they're not boiling it. It's not water that you'd be, say, removing, you get grounds. So that's how they remove it. And that's how you get decaffeinated coffee, is using supercritical CO2. There are other applications where it's useful that are a bit more high tech, but mundanely, we use it to remove caffeine from a lot of things.
There we go. Another video down. No participations on this one. Participation 118 is what we're looking for questions on. That'll be due Tuesday. So I got more videos to find more questions. See you in the next one.